Hello and welcome. Welcome to another lecture series for Engineering Mechanics Second Dynamics. Today we will be discussing about radial and transverse components of vector. Let us suppose a body is moving along the curvilinear motion forming a polar coordinate system. It is at point P for this time instant and has r and theta. We mostly use radial and transverse components to define velocity and acceleration for particles which follow the polar coordinate system, which is in function of r and theta and not in usual Cartesian system. The vector ER is directed along the r, which is our displacement, and E theta is directed along the angle. Here is theta, which means that the E theta vector will also be directed towards the angle, and ER vector will be directed along the displacement. Let us make a simple diagrammatic representation for the radial and transverse component. At position O, the vector ER will be directed towards this direction, and E theta will be perpendicular to it, directing along this direction. After a certain time instant where the points are very close to each other, in this motion, in this path, a ER dash vector introduces itself. Here we get del ER, which is the difference. Simply following the triangle law, we know that this ER plus del ER will be equals to ER dash. Now let us complete this triangle for E theta vector. For very small angle which is moving constantly from here, if we represent it using this pen, if it's moving like this, which means it's going in this direction, the increase in angle is denoted by del E theta, and this is E theta dash. Therefore, this is E theta, this is E theta dash, and it is represented, the difference is represented using del E theta. For solving the numericals for this chapter, we need to remember two major relations, which are differentiation of vector ER with respect to angle is equals to E theta cap, and dE theta by d theta is equals to negative of the radial component of the vector. Using these two relations, we'll be simply able to derive velocity and acceleration for radial and transverse components. Now, let us go through the process of deriving velocity. We know velocity is equals to differentiation of displacement with respect to time. We know that our r is equals to RER. Our r is going along this direction, is represented by using this component of vector. Therefore, our displacement is simply equals to the magnitude times the vector representation. Therefore, we differentiate this with respect to time. We will be able to get this relation using a series of differentiation process. That is, first, the product rule of vector. First, with respect to ER, we separate ER. dr by d theta is equals to r dot, which is our velocity, plus r times der by dt. We use the chain rule, and what we do is separate der by d theta dot dt by d theta by dt, which simply gives us the previous term. Now, using the relation above, we will be able to write der by d theta as E theta, the angle component of the vector, and d theta by dt as theta dot, which is the change of angle with respect to time. Therefore, we have r dot er plus r theta dot e theta. This is the radial component of the vector, and this is the angular component of the vector. We know Vr is equals to r dot, and we know v theta is equals to r theta dot. For acceleration, again differentiating velocity with respect to time, here we have taken out er, and then we differentiate with respect to r dot first, which gives us r double dot, which is equals to acceleration, plus r dot times der by dt, which on chain rule again gives us der by d theta gives us e theta. We put e theta, and doing the differentiation of this term, what we'll be able to write is r theta dot d theta by dt. We will be simply able to replace it by negative of radial component of the vector. And differentiating r and theta dot once using product rule, we will be simply able to rewrite this relation, and hence we get to this result. The radial component of acceleration is equals to r double dot minus r theta dot square, and the angular component of this acceleration is equal to 2r dot theta dot plus r double dot theta double dot, which simply gives us the relation to calculate the velocity and acceleration for tangential and normal components. Hope you follow up with other videos from this series. Signing off.